speaking about computable entanglement cost.
Thank you very much. Thank you all for coming. And of course, let me thank the organizers for assigning me the 9 a.m. session after the conference dinner. So yeah, today I'll be speaking about a joint work with Ludovico, Lami and Francesco, Mele, and it concerns quantum entanglement, which is something we all know and love. But in many setups, in many algorithms, or in many protocols, entanglement comes in the form, or is required in the form of these maximally entangled states. So here's the 2-qubit maximally entangled state, or the EBIT, the EPR pair, the singlet, has many different names, but that's what is really needed to use entanglement in practice very often. But of course, in a lab, what we actually get is a noisy quantum state. So how do we connect these two concepts? Well, we can, to understand the entanglement content of a noisy state, what we can say is we can ask about how many of these maximally entangled states we need to prepare a given state. So this kind of notion allows us to easily compare the entanglement content of different states, because one can be more expensive than another. And this is essentially, this makes the maximally entangled state function as a unit of entanglement, like a discrete unit of entanglement. But to make this notion formal, there's an issue when you try to formalize this, because say that you have a state rho which requires 2 copies of the maximally entangled state to prepare. But what happens when you ask to prepare 2 copies of rho? Well, of course, you can do it with 4 copies of the maximally entangled state, but maybe you can get away with fewer. So this makes the notion of entanglement cost difficult to formalize, because to understand it, to understand the lowest cost of preparing a given state, we really should be considering many copy transformations and asking about the lowest rate at which we can, like a rate per copy, which is required to prepare a given state. So the entanglement cost of a noisy state is defined indeed as the least choice of such m and n that we can do this. And if you think of m, so the number of maximally entangled states, as a function of n, then this is essentially taking a limit as n goes to infinity. And that is a big problem, because, well, to understand the really truly operational properties of entanglement, we have to take the limit, or many copy limit as n goes to infinity. And that causes a lot of different issues. And so the main issue is, to formalize it, I'll have to explain a bit more about what this blue arrow means that I was drawing in this schematic pictures. Usually, this arrow is taken to be the set of so-called local operations in classical communication, or LOCC. And this is a very natural setup when we deal with 2 spatially separated parties. They want to manipulate their shared entanglement, but they do not want to, they only want to use local operations on their own systems. So indeed, if you consider these transformations, then the cost is known. We have an exact expression for the entanglement cost. It is given as this function. This EF there is entanglement formation. If you don't know it, it doesn't matter. The point is that we have to evaluate a limit with many copies of rho. And this procedure is known as a regularization. And this is the curse that essentially makes it impossible to understand any asymptotic properties of entanglement. Because to evaluate this, you may have seen similar expressions, for example, for quantum channel capacity. So this is like a notion that really is frequently encountered in quantum information. But these expressions are uncomputable in general. Clearly, even if you can compute a function, for example, this EF, even if you could compute it easily for a single copy, just the fact that you have n copies, that makes the program, the dimension scale exponentially here. So the evaluation of this is essentially impossible, and we cannot even approximate these things well, because if you stop at any level of the hierarchy, the n, then you're not guaranteed to be anywhere close to the actual true value of the limit. So this causes a lot of issues. So we may ask, okay, well, how can we simplify the setting a bit to get computable, understandable formulas? Well, one thing we could say is, okay, one thing I was hiding in this arrow is, usually when we deal with conversion of many copy states, we allow for some small errors as long as they vanish asymptotically, because we are dealing with limits, so it's fine to have some small kind of fluctuations, essentially. But you could say, okay, no, we don't allow any error anywhere in this process. We say everything has to be done with 0 error, precise, exact transformations. Maybe this could simplify. It does simplify the mathematics in a sense, but the asymptotics, we just get a different regularized expression. Here now it depends on the Schmidt number or the Schmidt rank of a given quantum state. So yeah, it's not quite computable either. And it really seems like this curse of regularization is a bane of existence of any quantum information scientists working with entanglement. But what really is the problem? What is the reason why these expressions are so difficult? Maybe, one could think, maybe it's because of the choice of LOCC operations. So it is indeed a terribly difficult set to understand, to try to simplify it mathematically, even. Like, we really have very little understanding of the structure of the set of LOCC. So we could say, okay, well, let's try to use an approximation. Let's try to relax it a bit and see if we can simplify the theory in a essentially approximate way. So to do this, we will introduce the concept of the partial transpose. So I will use gamma to denote partial transpose, and it's just an operation that takes a transposition in some basis of one part of the bipartite system. The crucial property of this function being that if a state is separable, then its partial transpose is positive, so it's a valid quantum state. So with the way to think about this is essentially that the set of PPT states, or positive partial transpose states, is an approximation to the set of separable states. And indeed, it is in many ways, it is a good approximation, and it shares similar properties to separable states. For example, I mean, these states are essentially weakly entangled. No entanglement can be distilled from them. So essentially, they are useless for certain tasks like entanglement distillation, or indeed, for example, in teleportation, they do not provide any advantage over separable states. So yeah, they are very, very similar structurally and to separable states. So indeed, what we could do now is to say, okay, well, what we will do is to say, to consider LOCC operations, and then in addition, allow these PPT states as an additional kind of resource that the parties in Alice and Bob can use essentially to communicate, to manipulate their entanglement. And this leads to the notion of PPT operations introduced by Raines in 2001. And okay, so this set of operations you can think of, okay, mathematically you can define them as all operations or all channels, lambda, which essentially preserve the set of PPT states. So if a state omega is PPT, if you act with a channel on it, it remains PPT. Even more simply, we can think of this as you can just check the Choi-Miałkowski matrix of your channel, and if that has a positive partial transpose, then this is an equivalent definition of these operations. So essentially, the point is that they are simple to characterize. This is like a nice SDP or semi-definite programming condition, and the structure of them is very nice. And in the same way as separable states approximate, PPT states approximate separable states, PPT operations approximate LOCC. And indeed, now what we defined, finally, the main quantity we want to study, it is the exact asymptotic cost of entanglement under these PPT operations. So it is the least rate at which we can prepare copies of a given state row using copies of the maximally entangled state. So this may look like a mildly arbitrary choice and simplified choice because, okay, we relaxed our setting, we considered PPT operations, but this has a long history in quantum information. And so indeed, it was first studied in the work of Oudenaarde, Plenio, and Isert, where they showed that this quantity, even though it's an asymptotic and kind of difficult-looking quantity, it can actually be computed for a certain class of states. And this class of states are states with zero binegativity. So this quantity, you notice, you take a state, you take the partial transpose, then you take the absolute value, and then you take the partial transpose again. Okay? This has no physical meaning at all, or at least that as far as we know. But if this is true, so if this operator is positive, then the cost equals exactly the negativity. And negativity is one of the most frequently encountered monotones for measures of entanglement because it's just so simple. It's just the trace norm of the partial transpose of the given state. Yes, of course, but this is nice. So this allows us to compute this cost in some cases, but not all. And the question is, how can we evaluate this quantity for all states? And indeed, this was studied very recently in a paper by Xin Wang and Mark Wilde, where they showed that this cost, the exact asymptotic cost, it can be written in this regularized form. So we have to compute this limit as n goes to infinity of this function, e kappa. I will define this shortly. The point being that, again, this is just impossible to compute in general. Like if you look at it, this program becomes, again, the scaling is exponential dimension and things are messy again. So we don't really seem to get a nice simplification. However, what they claimed in that paper was also, there was one more thing they claimed, and that is that this function actually is additive. So if you evaluate it for n copies, it's the same as just taking n times as the single copy value. And this, of course, makes this regularization trivial. There's no need for it anymore. So the claim was indeed that the cost for any state it equals this monotone, this measure kappa. Now the issue is that there's actually a mistake in that paper. The proof is incorrect, and that property is not true. We do not get rid of we cannot get rid of this regularization. And just to justify, because so the fact that this is not true, this kappa being an additive function, this is our first result actually, and I will just quickly mention this because it's a very nice construction that we use to show it. Because remember that if a state has this binegativity being 0, so it's positive, this thing is a positive operator, then the cost simplifies. So if you want it not to simplify, we have to look for states which do not satisfy this. And to construct such a state, we do the following. So consider this 2 qubit space, and you can write this in computational basis, and you just fix ones on the diagonal and then some strategically placed ones on the off diagonal. Now, why do we do this? Well, okay, we define this two qubit, the punch card state, or well, it's proportional to a state at least, by punching 2 holes in the diagonal, essentially. And why do we do this? Well, because if you take the partial transpose of this thing, then all that happens is that off-diagonal elements just shift. Now what we end up with is with this matrix. And now, if you take the absolute value of this now the only non-positive part essentially is this 2x2 matrix. So this just becomes its own absolute value. So the ones essentially move back to the diagonal. And now if we take the partial transpose again, then these zeros that we've introduced here, they shift back to the original positions. Now what this means is that what happens here, if you look at it, the positivity of this matrix is not difficult to depend on the positivity of the outer elements of the outer 3x3 matrix. And that is easy to show to be not positive, and indeed, so this binegativity of this is violated. And then if you just evaluate this quantity, then you can show easily that there's a violation of the claimed additivity. So yeah, just wanted to quickly rush through this for interested part of the audience. But the point is that we cannot get rid of regularization in the problem. So we do have to consider this asymptotic limit. So then, okay, well, but I promised you some simplifications, and we don't seem to get any so far. So what can we do? Well, let's think about it, because the cost, okay, the negativity is a very simple function. It crucially is additive for all states. So it's not difficult to show that always gives us lower bounds on the cost. On the other hand, this kappa that I will introduce in a second, I will define in a second, it's not additive, but it is sub-additive. So it always gives us upper bounds on the cost. And so the idea is then, okay, we have these 2 monotones, lower and upper bounds. How can we make them give us better bounds, like better lower and better upper bounds? And for this, we look at their definitions. So the negativity, as I mentioned, is just the trace norm of the partial transpose, but you can write it also as the semi-definite program. So it's minimizing the trace of this matrix, which essentially sandwiches from both sides the partial transpose of the state. Now, this kappa monotone introduced by Wang and Wieldy, it is defined very similarly, except that also, in addition, you impose that the partial transpose of that matrix, the sandwiching matrix, is also positive. So what can we do here? Well, clearly, the trick here seems to be this sandwiching operation. So the idea is essentially just to iterate that sandwiching. And so we define 2 hierarchies of semi-definite programs. One is this chi hierarchy, parameterized by parameter p, and the idea b is simply that we do the sandwiching p times. That is essentially the whole idea. Now the kappa hierarchy with the parameter q is, again, we just do the sandwiching idea. So we just take many of these sandwiching matrices, we do it one by one, and then finally at the end we impose that the final sandwich has a positive partial transpose. And again, I want to stress that these are all SDPs, so they are efficiently, computable in the polynomial dimension of the system. Yes, and so, okay, so the crucial point being that, indeed, these quantities generalize the relation, the lower and upper bounds. So indeed, we get that these hierarchies provide increasingly better lower and upper bounds. And this already is non-trivial to show. This requires some playing around with the SDPs. But it's not quite already what we wanted, because we don't know how close we get to the actual value of cost. We do get nice lower and upper bounds, but we don't know how close we get. So, however, our result is that indeed, in the limit, as p goes to infinity or as q goes to infinity, we get an exact expression for the entanglement cost here. So both of these hierarchies converge to the true value of the cost. And okay, so this is already a new expression, a completely new expression for the cost of entanglement on the PPT operations. And this allows us already to show some interesting properties like continuity or additivity of the cost. But crucially, the crucial point here is that we rewrote, or we established an equivalence between this regularized quantity and these non-regularized expressions. So there is no longer many copies of rho that you have to consider here. So that is already something new. However, it's not quite what we need from like a practical perspective, because there's still this weird limit here. So you can ask, okay, well, we replaced one limit with another. How is this really helpful? And indeed, this is a good problem, a good comment to have if you did think that. So we address this by essentially establishing that there is no need to worry there. And for this, remember that the chi monotones give us lower bounds and the kappa monotones give us upper bounds. And now the key identity we establish here is that these two hierarchies can be related with each other. So we get upper bounds on the kappa monotones, which remember that they are the upper bounds on the cost. We can actually upper bound them with this chi hierarchy. And this already implies several things. Like, for example, if you take d equals to 2, then we get actually an exact expression for the cost. But it's not always this value. However, what we can show is that, okay, a way to think about this is if you rewrite this, if you think of this, how the difference of, I mean, essentially, how close are we to the true value of the cost at the pth level of the hierarchy? The point is that if you rewrite this, we get this expression. So essentially, you can bound the pth level error with the p minus 1th level error. And if you iterate this, what we get is that this, well, goes to 0 exponentially fast. And that is a crucial property, the exponential convergence to the value of the cost. Because what this means, and indeed what this allows us to establish, is that what you may have guessed from the title of the talk, the computable entanglement cost. So we do have an algorithm that computes, for any quantum state, that computes efficiently the value of the true value of the entanglement cost to any desired precision in time that is polynomial in the dimension and in the error, logarithm of the error. And look, I mean, this may look, okay, there's lots of weird powers and stuff, but the point is this is an extremely simple algorithm. The point is we only have to climb this hierarchy of chi or kappa up to some level to get the precision to be small enough. And the point is that this level of the hierarchy doesn't have to be so big. It is polynomial in dimension, or well, linear in dimension. And yes, and then you just evaluate this SDP. Then at every level, these things are SDPs. At every pth level, it's an SDP. So what you do is just choose any SDP solver, you evaluate it, and you get the expression for the cost to any precision. Yes, so this is indeed what the result, all the results of this talk essentially are combined here. The point being that we have a method to compute exactly this asymptotic entanglement cost. And so, yes, so it's effectively SDP computable. Now, to conclude, yes, so what I've told you about is that we showed a formula for the asymptotic zero-error PPT entanglement cost. And crucially, this formula has no regularization, and it can be evaluated to any precision in polynomial time. Now, this is interesting from several different reasons, and crucially, this is an operationally meaningful measure of entanglement, right? Because you remember, the entanglement cost is defined operationally as the least cost, I mean, the least number of essentially of maximally entangled states needed to get a given quantum state asymptotically. So this asymptotic measure is actually computable here, and this is one of the very first time in all of quantum information where a regularized quantity, which we do encounter these all the time, I showed you in quantum capacities, quantum entanglement manipulation, these quantities are generally uncomputable. But what we have done is we established a way to compute it, and interestingly, it's not that we avoided regularization. We just replaced it with a different optimization. But the crucial point is that the exponential dependence on dimension of the regularization is replaced with the polynomial dependence of this new hierarchy of semi-definite programs. And yes, that's kind of the new part here the novel kind of feature of this is that we don't have an additive expression for this. We don't have a closed form expression for it. So we don't really avoid the issue of regularization. We tackle it head on, and we just defeat this curse of regularization. Okay, there is still a potential for even more simplification here, because the big open question is, does this hierarchy actually stop improving at some point? We don't know this. We were not able to show, because essentially it may be that the cost equals exactly this P hierarchy at some P level. And we ruled this out for the first 2 levels, but already third level, we're not sure. We cannot rule out that already at the third level may stop, and that is just the formula of the cost. But I want to stress one thing. Even if this is true, it doesn't really improve the computability much, because we already have a polynomial algorithm for computing the cost. So this is still polynomial extension dimension. So it's just like aesthetically would be nice to show, but from a computability perspective, we already have a computable expression for the cost. So with this, I thank you very much.
Plenty of time for questions.
Thanks a lot for the very nice talk. I had one question. I had 2 questions. First is the exact, do we know how far the exact PPT cost is from the exact zero error cost, typically?
You mean LOCC or?
Yeah, only LOCC versus LOCC plus PPT. What can be the difference between these 2 costs?
I mean, in general, we don't know. But I guess you're asking if it's going to be like unbounded.
Yeah, maybe even for simple states, or they, how different. Has someone shown like these are actually just different, or?
I don't think we know much because of the fact that it's just uncomputable for LOCC, yeah, I don't think we know much about it, or at least, well, I don't.
And the second question to your hierarchy was that, in the current information game, when you're computing these, there are these examples where the current information is 0 for first k uses, k plus 1, it's non-zero.
Yes.
And I'm wondering if you can try one of those examples, like the choice state of the channel that gave that kind of example.
For the open question, you mean here?
Yeah.
Okay, well, yeah, this I cannot address now, but we can check that.
Yeah, I wonder if you. Yeah.
Thank you very much for the comment.
Thank you very much for nice results and the excellent talk. I have a question about the hierarchy. So you showed very quickly upper and lower bounds. So how does it capture the positivity, PPT-ness of you had an extra constraint in the upper bound. So I didn't get how the iteration captures that additional constraint. Can you comment on that? Like, why does it converge? Like, that's my question pretty much.
Why does it converge? Yeah. It converges because of this identity. This is the key identity that makes it converge. And the point is that, well, I mean, if you're asking for intuition for why this is true,
yeah. Yes.
Yeah, the form of the SDPs makes this true. I don't know if there's any. Yeah.
Thanks. Sorry. Yeah, somehow like if you. I mean, you want to turn this chi hierarchy into this kappa hierarchy. And for this, you need to take this last sandwiching operator and make it PPT. And there is a natural way of doing that by somehow adding some noise in an optimal way. And somehow you pay less if you do it for larger P. Because it's like at the end of the hierarchy, so you pay less. But that's how you pass from one to the other. Like the proof of the key identity is actually very, very simple.
Yeah, I mean the dimension you get just like it's like a worst case scenario with the dimension dependence here. Like I mean, yeah, but it's. This is like it's intuition. Like, do you have intuition?
No, I don't know, but this is the best thing.
Thank you to both of you. I have another quick question.
Yes.
So the fact that you can compute these things for PPT, for separable transformation, does it somehow imply that it's away from LOCC? Because it's very hard to regularize things for LOCC. And here somehow you have like overcome the curse, right? So
yes.
Does it mean that it's just not really physical transformations that you use here?
I mean, yeah, they are relaxation of LOCC, and they are strictly different. We have examples. Operationally, also, they are more powerful. It's just that they typically give us the best known computable bounds or computable understanding. And of course, that's the whole point, just to have any understanding of essentially what we get here is a upper bound to LFCC, and it can be tight, it can be not so tight. But if you allow this PPT as a kind of operationally motivated relaxation of LFCC, then we understand it exactly, and that's the crucial part. But if you, yeah, I mean, it is different, and we already knew this, and yeah, I guess this confirms that it's much more nicely behaved than LFCC. Yeah, that's I guess that's how I would describe it.
Thank you.
Thanks a lot for the talk. So about your open question, whether the hierarchy collapses, I was wondering what the reason is that you don't know, even for examples, because if you say that you can compute the different levels of the hierarchy, don't you have any example where like hierarchy levels 5 is not equal hierarchy level 6?
No, because I mean we can evaluate this for states, and we have counterexamples. Numerically, you can find counterexamples for the difference between like the first and the second level, for example. You can just generate states or try to come up with counterexamples, but we were not able to. We checked weirdly behaved states, you know, all the kind of the usual suspects, essentially, except for the ones that maybe where there was a suggestion here previously. But yeah, we just were not able to come up with a good counterexample. If you have ideas, please do check. It's a simple SDP, so you can play around with it if you find it, and it's, yeah.
Okay, thanks. Yeah. Okay.
Yeah.
Let's thank Bartosz again.